Hi, this is Dr. Marshall, and this is the first video of the 1-1 classifying matter discussion for chemistry. And if you're here, I'm assuming you got here by going to the chemistry homepage and then clicking on participation 1-1 assignment, and then printing out the worksheet and then going to the Nearpod demonstration or video or the Nearpod presentation and then clicking on the video. And so I'm headed to the Nearpod presentation right now, and come on, there it is. So we join, and the first thing that I need you to do is try to answer a question for me. We've previously talked about the concept that physical and chemical properties are most closely associated with either intraparticle or interparticle forces. And see if you can remember which is which. So I've said physical properties are most closely associated with, and I need you to circle, so take the drawing tool and circle either intraparticle forces or interparticle forces, and then the same for chemical properties. Okay, and don't worry, I'm not grading you to see which one you get right. I'm just trying to check for your understanding here. We'll get more in detail in this in a little bit. So go ahead and do that, and then submit, and then go on to the next page. So our learning target for this, the student will be able to define matter and its physical properties of mass, volume, and density, be able to state the units used to quantify these properties, and then use the mathematical formula showing the relationship between these properties to interpret and solve basic problems using these properties. And this is because matter is the beginning of understanding of all chemical knowledge. We need to be able to describe and define matter and things related to matter in order to begin to understand other things. So you'll be able to correctly write the definitions of matter, mass, volume, and density. You'll be able to match base SI units to corresponding quantities measured by the units. You'll be able to state why the official unit for density is not commonly used in chemistry and what unit is commonly used in its place. And you'll be able to use the density formula to solve basic problems involving mass and volume. Okay, so we classically define matter, and again, I'm going to use the notes function to write out answers here. So J. Marshall at Summit Academy Schools.org. And so our answer for this, we classically define matter as anything that has mass and volume. Okay, this is what goes in your first blank there. Okay, so hopefully it makes sense that in order for us to understand this definition, and especially dealing with some issues that we're going to have related to mass, in order to better understand this definition and help us identify issues we need to deal with, we also need to define the terms that make up this definition. In other words, I need to also define mass and volume. Okay, so we define mass as the amount of matter, how much matter is in the amount of matter in a quantity of matter. How much stuff is in a quantity of matter? How much stuff? And we have a specific unit in mind when we're dealing with this. The standard unit, the standard system of units the scientific community uses to quantify things in the natural world is called the SI system. You may think it's the metric system. It's the outgrowth of the metric system, but it's not the metric system itself. and this is also called the International System of Units. Now, it's not the IS system, it's the SI system, because the name in French is Système International des Unités, and I don't know how to pronounce that in French, but it's the SI system. That's the system that we use. It's the logical outgrowth of the modern or the metric system, and it's based on 7 base or core units of measurement and the ease of working with the number 10. So from the standard 7 units, a large number of other units are derived, and the word derived means built on. Okay, if something is derived, it's built on something else. And these core units are called base units, and units created from these units are called derived units. Okay, so the units that we need to be aware of, the standard measure of length is the meter. The standard measure of mass is the kilogram. Standard measure of time is the second. The standard measure of temperature is degrees Kelvin, and we'll talk a lot more about that later in the course. And the amount of substance, the standard amount of substance, is something called the mole. Okay, so moving on to the next slide then. These are the official or core units. Any other unit that we have, any other unit is based on these units. That's why these are called base units. We won't have any use for units of electricity, electrical current, or luminous intensity, but we will need to know the other 5, length, mass, time, amount, and the temperature. So those are the 5 that we'll need to know and have down. Okay, now if a measure of the amount of matter in a quantity of matter, if mass is a measure of the amount of matter in a quantity of matter, ask the question, would 1 gram of sodium contain the same number of atoms or same number of particles as 1 gram of gold? And here's what I want you to think about. The first thing I want you to think about is that the atomic mass of sodium is 22.99. Atomic mass of sodium is 22.99, and the atomic mass of gold is 196.97. Okay, and so if I think about the fact that 1 particle of gold is a lot bigger than 1 particle of sodium, it should make sense. It will take fewer, let's say it this way, because each particle of gold is more massive, it will take fewer particles of gold to make 1 gram than particles of sodium. Okay, so since gold particles are so much bigger, it will take fewer particles to make 1 gram than it will particles of sodium to make 1 gram. Okay, so no, the number of particles in 1 gram of sodium is not going to be the same as the number of particles of gold in 1 gram, and the number of particles of sodium is going to be greater than the number of particles of gold. This is confusing because gold is more dense, so we think of it having more particles, but per volume. But when we ask the question this way, how many particles will be in 1 gram, it's going to be that there are fewer particles of gold in 1 gram than there are of sodium. And there's a reason that I'm asking this question, and let's go to the next slide to figure out why I'm asking this question. So when we have a chemical reaction, we ask the question, do substances react according to how much mass is present or according to how many particles are present? Do we say so many particles of A react with so many particles of B, or do we say so many grams of A react with so many grams of B? And if you think about chemical equations that you've seen, you think of the fact that we're asking about how many particles are reacting. Okay, we would say 2 particles of hydrogen react with 1 particle of oxygen to give me 2 particles of to form 2 particles of water. Okay, so we don't say so many grams of hydrogen react with so many grams of oxygen to give me so many grams of water. We say numbers of particles, right? Okay, so we're going to say particles. And the reason that this is a problem for us in the laboratory, this is really significant in the laboratory. The reason that this is so significant is we cannot measure numbers of particles reacting in the laboratory. We can only measure mass amounts. Okay, so we're just looking at this in a couple of different ways here. If I'm asking how much of something is present, I can ask how many particles are present, or I can ask how many grams are present. It's 2 different things, right? It's 2 different ways of saying the same thing. I have so many particles, or I have so many grams. But we know that we're talking about number of particles when we're talking about chemical reactions, but I can't measure numbers of particles. Okay, I can't measure the number of particles. I can't go to the lab and say, okay, let's have 6 molecules of hydrogen and 3 molecules of oxygen. I can't pull out 6 molecules of hydrogen. I have to measure out a number of grams of these things. Okay, so what we're going to end up doing then is constantly converting from numbers of particles in our chemical equations to numbers of grams. Okay, so we can't measure numbers of particles reacting in the laboratory. We can only measure mass amounts. We will constantly be converting back and forth between numbers of particles and numbers of grams. Okay, so that's a problem that we're going to have, and that's the significance of mass versus particles. In the laboratory, we'll use a couple of different types of balance to measure mass. This is an electronic balance. This balance will be what we use the most. It measures to tenths of grams, which may not always be sensitive enough. And then this is a triple beam balance. This particular triple beam balance actually happens to measure to hundreds of grams, so that's a little more sensitive, and that's usually what we'll be wanting, hundreds of grams. We don't have one of these available to us, but there are balances that are even more sensitive, and this is called an analytical balance, and this measures to hundreds of milligrams. So to 3 decimal places is a milligram. I can go beyond that and measure to hundreds of those. So literally we can measure to hundreds of thousandths of a gram. Okay, and that's what this could do if we had one. Okay, but they're very expensive. So coming up on 15 minutes here, so we're going to have to stop this video and move to the next one.